All right, good morning. We've got some folks online, and we've got lots of folks in the room. How's breakfast? Yeah? It works. I'm going to see if my gizmo wakes up this morning. It's still early. There you are. Hello. My name's Richard Campbell. This is a talk I've done a few times, although it keeps evolving on me. I sat down with it the past couple of days to say, what would I say now? You know, I started writing the first version of this in 2019. We were all so happy and carefree. So it's been a crazy few years, but I come from British Columbia. That's my house on the left, my neighbor's place on the right. We call this the Animal Highway. And this is a Wednesday morning. And Wednesday morning in my town is garbage day. And so I didn't know until I put the camera in, but I have bears come and visit every week to see if I put out my garbage early. They don't mess around. Now, look, I'm in Minnesota. This is not that impressive to you. You should see the Australians. They go nuts for this. They got all the poisonous spiders and snakes and stuff, but you show them a bear, they go crazy. But it's Minnesota. You get these in the city, right? They're around. But you notice he's standing right at the front of it. He's literally surveying his domain right now. It's like, who put out the garbage? Anyway, I make a lot of podcasts. Any .NET Rocks listeners? Oh, wow. Okay. Thank you. And Carl's here too. He's doing his Blazor workshop, so he's working way harder than I am. Carl started .NET Rocks back in 2002, which predates the word podcast by like 3 years. I came on board in 2005 on show 100, and I think we're at 1815 now, so done a few. And a few years ago, I started Run As Radio because I felt like the sysadmin audience wasn't being well represented. And so every Wednesday since April of 2007, I've put out a Run As. So we're at about 850 of these. Free to download. You can get them on any of your favorite. They're on Spotify and all your favorite players. We interview smart folks from the industry, right? And for a few years, we made a show called The Tablet Show. It is this brief period around 2011 when we weren't sure if .NET rocked. It was a scary time for all of us. But by 2014, it's like, okay, .NET's fine, and we rolled all that back together again. And this talk's really built on all of the stories that I've collected being a podcaster, talking to really smart people, lots and lots of them. But I will reflect on Niels Bohr, who said, prediction is difficult, especially about the future. Not that I know what else you would predict. And that's the guy who came up with the atomic model. Like his PhD thesis is the idea that like the proton in the center of the atom with the electrons around. That's Niels Bohr. That's his stuff. So, which is all pretty recent. That's like the 1910s, like only 100 years ago that we've really got into the atomic model. And look at the mess we've made. Because you can't talk about the future of software without talking a bit about its hardware as well. And we're definitely pressing against some interesting limits when it comes to hardware. And that's going to be reflected in our software over the next few years. We know the cloud is a big deal, right? If we talk about the previous decade, like what's really happened the previous decade, but we all got into the mood of using somebody else's computer by the minute, on demand. So that's kind of table stakes today. You've got to have a cloud strategy, even if that cloud strategy is no cloud, please. It's still a strategy. Also, smartphones. For better or worse, the phone has penetrated human civilization. There's about 4 billion of them in use today. That's pretty much one for every adult human. We just tipped 8 billion humans like this week. Congratulations. Good news is that it only took us 12 years to get from 7 to 8, and that rate does seem to be declining. So it's going to be a while before we get to 9. But, you know, new markets. And the combination of cloud technology, smartphones, and various other bits and pieces have meant we've got an awful lot of data. Some people call it big data. It's just a lot of data. I'm not saying it's good data, but we've got a lot to munge through, for better or worse. And these are just trend lines, and they're easy ones. More compute, more devices, more data. That's pretty obvious. There's not really hard things in any of that. Obviously, that's going to happen for the next few years. But what's actually going to change in this next 10-year period? One aspect is the end of Moore's Law. So our friend Gordon Moore, the reason we're all here ultimately, one of the guys who helped form Intel, he made this observation in 1965, so a really, really long time ago, that for the same amount of money in a piece of substrate, in a piece of silicon, he could put twice as many transistors in. every 2 years. That's basically what he said. They didn't call it a law because it's not a law, right? Gravity's a law. Doesn't matter whether you agree with it or not, it's there. The only way we get this doubling effect is a lot of people work really hard. The good news is it's worked out pretty well. This is data pulled right from Wikipedia. It's just an exponential graph on the left side, starting with the 4004 processor in 1970 up until today. The number of transistors has kept growing at an exponential rate. We're at tens of billions now. Now, if without that exponent on the left side, the graph is kind of stupid, right? Because the numbers are irrelevant until you get to the last numbers because they're so huge. But not everybody's a numbers person. It's not an easy way to look at it. So a better way to look at it, this is the way I describe it. I show you one of these. What's this? Warp drive from the Enterprise? No, that's this. This is a Cray 2 supercomputer, circa 1985. This was the most powerful computer in the world at the time. Only a few hundred of them were ever built. They were about $16 million in 1985 dollars. They were cooled with mineral oil because they ran so hot, they were constantly pumping mineral oil on them to keep them from melting down. It's curved to keep the wires as short as possible. The speed of light mattered inside of that supercomputer. And it had 1.9 gigaflops of processing power. It would do 1.9 billion floating point operations per second. They modeled nuclear explosions with this. These were in universities and governments. They were these incredibly powerful machines. Now compare that to an iPad 2. So now we fast forward a few years. 26 years later, in 2011, Apple releases the iPad 2. It's $600. Keep it away from liquid. Battery's pretty small, 1.9 gigaflops. And you play Candy Crush on it. You hand it to children to keep them quiet. And it works. But that's really the application of Moore's Law, right? That 26 years later, the computing power of the fastest supercomputer in the world is a device we give to children. And that's not fast. That's 2011. That's now 11 years ago. If you talk about a consumer compute device, a maximum performance consumer compute device, look at a video card. Look at the GTX 4090, if you can find one. So that's about $1,600 retail if the eBay scammers aren't marking them up. Although I guess we're out of Bitcoin, so it's getting easier to find one of these. 16,000 cores in it. 82 teraflops. So that's 40,000 times faster than the iPad 2. And that's a commercial retail product. You can buy this at a Best Buy, right? And by the way, this thing's 450 watts by itself. So if you're going to put one in your computer, make sure you got a big power supply because you still have a CPU. And if you're really a nut, buy two because you can crossfire them and connect them together. I don't know why you would, but you could. Top of the line compute devices today, anywhere in the world, are the new generation supercomputers. The current leader is an American computer. It's a race between the Chinese, the Japanese, and the US to build the fastest supercomputers. And at the moment, in Oak Ridge Labs, down in Tennessee, the Frontier supercomputer is the current leader. It's 1,100 petaflops, so 1.1 exaflops for $600 million. It takes 20 megawatts of electricity, so bring your own nuclear reactor, and takes up about 8,000 square feet, so not exactly for the home. But that's 14,000 times faster than that 4090, or 600 million times faster than the iPad 2. Welcome to Moore's Law. And yet it's ending. We can't keep going on this curve. I just can't stay that straight line forever. Why? Well, the way that we increase computing performance is by putting more and more circuitry in, more and more transistors in the same die. We stopped making processors faster a while ago. We kind of topped out around the 4 gigahertz range. After that stuff just starts to melt. And so we put more and more processors together. That's what that supercomputer is really about. It's hundreds of thousands of cores that all work together on these crazy problems. In 1970, when the first processors were made, they were using a 10 micrometer process. You could almost see the transistors. Today, we're talking about 5 nanometer. And a nanometer is just one of those crazy numbers, right? It's too small to conceive of. We have electron tunneling microscopes that allow us to see down to the individual transistors 5 nanometers across. But a nanometer is another one of those, it's a billionth of a meter. Well, I'm in America, you don't know what a meter is anyway, right? Meters like this, it's roughly 3 feet. So if you're going to cut that into a billion pieces, those are really small, right? And one of the ways I try and describe this is I use seconds. If I ask you to wait for 1 million seconds, how long am I asking you to wait for? It's about 11 days. It's a long time. If I ask you to wait for 1 billion seconds, that's 32 years. So, 1 second is to a nanosecond, as 1 meter is to a nanometer. Compare that to 32 years to a second. It's a crazy small amount. And at 5 nanometers, you start to care about the width of atoms. So this is from the IBM's scanning tunneling microscopy. They're actually taking a picture of the substrate. The yellow bumps you're looking at are silicon atoms. Silicon atoms are 111 picometers across, roughly 0.1 nanometers. Those blue holes, those are phosphorus atoms. That's the doping for P-type substrate when you're making a microprocessor. It's 40 atoms across at 50 nanometers. We're running out of atoms. You just can't get a lot smaller before quantum effects and electron tunneling and so forth just take over. So we're getting to the end of Moore's Law. Now, is that a terrible thing? No, not really. It changes stuff. If you can count on the fact that you're going to have more compute every 18 to 24 months, you're disincented to do other things, like improve architectures. And that's why Intel still makes essentially the x86 chipset, right? The instructions that were put into the 8086 back in the 1980s, still there. It's all about compatibility. And so this layers of architecture they've stacked on top of their processors over the intervening decades have built up a lot of cruft. It's actually a lot of shuffling around inside of a modern Intel processor to be as fast as it is. Now compare that to the ARM architecture. Because it started later, because it could count on 32-bit wide buses and 64 buses, they've simplified the architecture. And so you consume a lot less energy for the same processing workload in modern architectures. And largely we're insulated from that as software developers. We don't really care about the hardware anymore. For the most part, we just write our code and it runs on all these platforms. That's magic. It's also inefficiency because we can afford it. Maintainability is more important than raw performance all the time. But when you look at the current leading edge chip in my mind is Apple's M2. That's 5 nanometer process. It's about 20 billion transistors in that package. And that's an 8-core CPU, a 10-core GPU, a 16-core neural net tuned processor, and a whole bunch of cache. They've integrated all into one chip, and if you've played with the latest generation Apple machines, they're some of the finest computers made today. They don't need to be much smaller than 5 nanometer. I don't know how much we're going to get from it. But the fact that that's running out means that our work's going to change a little. We're not going to count on having a lot more compute everywhere. It's just going to spread out. And the nice thing about the future is that it's already here. It's just not evenly distributed. There's lots of places where you're not running 5 nanometer gear and so forth. And so over the years, that's going to propagate. This stuff's only going to get cheaper. I don't know if you've looked at the latest Macs, but there are many things, and cheap is not one of them. On the next layer, talk a little bit about networking. Everybody really excited about 5G? You know, when I started doing this talk back in 2019, 5G was in the news. It was very heavily hyped, and now it's here, and nobody cares. Like anything that works, it's just not that important when it works. It's like air. If you've got it, it's great. If you don't have it, you're pretty unhappy. Connectivity is the same thing. I mean, 5G was kind of raced out into the market by the telcos because they needed a competing product. They needed to show they were getting faster. The problem is that wireless has physics problems. If you want to get more data per cycle wirelessly, you have to go up in frequency. So our old 2G cell phones back in the day were 450 and 900 megahertz. And then our 3G phones got up to about 2 gigahertz. Most 4G was 2 gigahertz. 5G is 22 gigahertz. You can pack a lot more data at those high frequencies. They just lose penetrating power. When we were at 900 megahertz, you could take a phone call in your basement and you expect it to just work. Could move a lot of data, but it was reliable. We had enough problem with 2G, with 2 gigahertz, moving up a bit, doesn't penetrate near as well. 22 gigahertz has problem with things like leaves, windows. I had a speed test set up on my 5G phone, and I was literally outside facing a 5G tower. And I'm getting epically fast speeds, like just racing along. And then I turn around, turns out I can block 22 gigahertz. So part of the challenge of the 5G network is they need a lot more cell nodes closer together because the range is limited, the penetration is limited, and cell nodes get saturated. And then so we're not seeing the full potential of 5G yet. But the power consumption is pretty low. The devices are pretty compact. And so more and more we're being able to put these chipsets into almost anything. The biggest thing that 5G gives us more than anything is making 4G really cheap. You're starting to see this if you buy a new car today, that most cars just have a cell network built into them. You may not have access to it, but the car is sending telemetry back to the factory by default. The 3G and 4G stuff is so cheap, the car company just includes it. Satellite network is real. Starlink has happened. Anybody got one? I mean, I'm in the part of the world where you might actually try this. I've got one at my cabin on the coast in British Columbia. At this point, Elon is the largest satellite operator in the world. There are 3,100 operational Starlink satellites. All the other satellites in operation around the planet is about 1,700. So yeah, dude's got a lot of satellites. They're all the same. They're not very interesting. They're in a series of tiers. But the bottom line is you can take out this pizza box sized dish, set it up, point it at the sky, it'll adjust itself, internet. Decent internet too, about 20 milliseconds of latency, and depending on where you are, 100 to 200 up and 100 to 400 down. Like a cable modem. It's not as good as fiber, but it's pretty good for not needing any wires at all. And the next generation stuff he's talking about will work directly with cell phones. All he's got to do is stop working on Twitter and maybe we get some of this stuff done. Yeah, but let's speak to what these things combined really mean. Cheap compute, lots of it. Cheap connectivity, and lots of it. Networks almost anywhere. This is this idea of ubiquitous computing, that we just have compute everywhere. It's going to affect us as developers. These days, the little chips that end up in things like dishwashers and so forth, they can run .NET. They've got the ESP32 is $10. If you buy it in quantity, it's less than $1. So why would you put anything else in an appliance? And so it's a reality that we can expect IP addresses in every appliance. I'm not going to say if that's good or bad. I'm just saying that's the path we're on. And it means that for us as developers, there's a tremendous number of places to do work in. Do I want an IP address in my toothbrush? No. Yeah, but am I going to get it? Probably. That's the cheapest compute. All right, one other scene setter before we start digging into specific technologies. Got to talk a little bit about the pandemic. I mean, we're getting down there now. It turns out it's not just going to end, it's kind of fade away. It's getting less and less interesting. We still have people getting sick and dying. I mean, that's the truth. We did this great cloud migration. Our friend Satya told us that, in March and April of 2020, in 2 months, 2 years of cloud migration happened as we pushed everybody to work from home, and a whole bunch of companies have said there's no way you can work from home said, hey, you're going to work from home. Now, that's not a big deal for us. If you're a developer, you may have been working from home long before that. It's a lot of productivity around that. I can't wait to write the history of Zoom and how that evolved. Because we clearly went through distinct phases. There was the you're muted phase. Then there was the turn off your filter, you're not a cat phase. And then there was the turn off your camera, nobody needs to see that phase. Although there was also in between that, everybody show your pet phase, and everybody show your kid phase. That's the fun part about the pandemic. But now we're getting into the really hard part, which is the economic impacts. Now, we could say, is this the pandemic? Is this inflation? I don't even go into that. That's not the important part. The important part is that companies are uncomfortable. And when they're uncomfortable, they get stingy. They spend less money, right? It's caution. They're not sure what to do. Now, this hasn't happened for quite a while. I have the good fortune to have been in computing for more than 40 years. And so I've gone through a few downturns. And it's not like technology stops when the economics get a little tougher. It's that it gets focused. We start caring a lot about return on investment. And we haven't had to do that for a long time. We've spent decades now in kind of a growth, build whatever you want, do experiments, let's try the new thing. Artificial intelligence is a good idea, crazy mindset. When we get into a downturn phase or an uncertain phase, we start thinking about the important parts of software. And in my experience, software can really only do two things. It can increase the efficiency of an organization. So fewer people can do more. Or it can measure that organization more precisely so that you can find opportunities to make more. Anything else is kind of moot. So if you're nervous, and seeing the layoffs that's going around in the big tech companies right now is pretty nerve-wracking, right? If this is true that Elon actually laid off half of Twitter's developers by stack ranking them by the number of lines of code they wrote, that's going to make Harvard Business Review of one of the dumbest things you could possibly do. I don't know if it's actually true, but as companies get nervous and they try and find ways to cut back, the people they're going to look to are the ones that don't seem to provide value to the company. How does your company make money? Because we're often removed from that as developers. We rarely directly make money for the company. Typically, we build tools that help others make money or reduce the cost of operations. If you pay attention to that and you make sure that that's the stuff you're working on, you're very, very valuable to an organization, including in the downturn times. So it's worth your time to focus a little on how does my company function, what's important to it, and how do I contribute to that? Because we can help companies get through rough times by helping them be more efficient. But if we're not working on those problems, we're not helping the company and we're not helping ourselves. Okay, let's talk about technology. The browser continues to be the winner. For better or worse, when it comes to building, especially in-house software, we tend to use the browser. That does not seem to be changing. There's a few good reasons for this. It's not JavaScript, right? What's the good news about a browser? All the machines already have one, nothing to install. Nothing to upgrade. It pretty much handles its own upgrade process. Anybody who opens up any of your web apps immediately gets the latest version. So all that versioning stuff goes out the window. By default, it tends to restore stuff only on servers. Good practices, natural security model, natural perimeter. You don't have to deal with a lot of that. It's almost worthwhile working in web development. The good news is also that we've built some pretty good frameworks and we continue to build more. The rate's slowing down, thank goodness. But you probably work with one of these if you're a web developer because they're efficient. They're a rapid way to build the kind of code your organization needs internally. This is going to continue. It is the most productive way to build internal apps and some external stuff as well. We've got the progressive web app, which is really just a set of rules for how we make regular users not understand they're using a web page. Right? Give them an icon, now they're happy. Right? A little bit of a manifest, that's all you need. Now, there's a bunch of other cool stuff going on in the BWA, things like queuing and disconnected behavior. Not that anybody really does a lot with that. It's so much easier just to always be connected than it is to try and figure out how to make a disconnected client that works. And if you've been playing with the latest stuff, you know that our friend Steve Sanderson, and he hates when I do this, a few years ago, it was actually 2016, took this WebAssembly standard, found a weird version of open source C# and made C# run in a browser and blew Microsoft's mind as well as our own. But it took a few years for Microsoft to take it seriously, but today we know it as Blazor. And my friend Carl is teaching a class on it this week, and it's C# in the browser. But WebAssembly is nothing specific to Microsoft. WebAssembly is part of the browsers. That's why there's Go. and several other languages that you can now work in the browser. So the browser's increasing its ability to serve a variety of developers, that you can program whatever language you want. Effectively, WebAssembly is simply saying the place where JavaScript lives is a set of hooks, put what you want in there. We're still at the beginning of this. What we're going to see with WebAssembly in the next few years is going to be impressive in our ability to build more software. Whether you want to go down the Blazor path or not, we're going to see more options around all of that. I will take a few minutes here to make fun of Web3 because it's easy at the moment. There's a couple of bits of it that make sense, and none of them involve NFTs, okay? The decentralization mindset is a logical swing away from Web 2. Web 1 was the server under your desk, right? In the 90s, in the early dot-com boom, we ran our own hardware for the most part. Then we found out that was really hard and expensive to do well. And so Web 2 said, we'll run it on Facebook. That's a good idea. Give up control entirely, live in other people's walled gardens. And now we're pushing back against that again to say, hey, maybe we should have a bit more control about where our stuff runs. That doesn't mean it isn't going to run in the cloud, and we don't necessarily own the cloud, but that's a little bit more of a neutral ground than a site that literally makes its money by selling you as the product. I think we're kind of done with that. I don't have a big problem with blockchain. Blockchain is an interesting technology. It only applies in certain cases. It's not the default for anything, but its ability to create a public record of transactions is useful. And so for certain applications, that makes sense. I look at it as the same relationship that BitTorrent had to Napster. Napster was effectively a criminal organization. It was hurting a group of companies none of us minded hurting, the music industry, but it tainted BitTorrent, which was actually a very cool technology just associated with stealing music. And blockchain has the same problem. It is associated with crypto. And if you have FTX crypto right now, you're a bit sad because that's a lot of value that just disappeared. But don't blame the technology. Blame what people did with it. We're still feeling around for what this stuff actually is. And those two main bits, this idea of token passing and creating a public record and being more decentralized, they're motions that will continue. But it's never a simple path. And so we're seeing mistakes being made along the way, some more intentional than others. .NET's having a good day. We just shipped .NET 7. We say we. I didn't ship anything. I got to be part of .NET Conf. That's fun, but that's just me being a dancing head, right? But some really, really smart people working at Microsoft work really hard for a long time to push out features every year. It's going to continue for the foreseeable future. .NET 7 is a very performant version of .NET. I hope you're having some fun with it. It's not the long-term support version, so many companies hold back on these non-LTS versions. They're going to stay on 6 if they've even moved off of 4.8. Lots of people are still living happily in 4.8 because you know what? Web Forms works, and it ain't coming, right? Like, it's really not coming. So how do you move off of any of that if you're going to at all? Like, does it make sense? And that software functions, so it's hard to get away from it. Microsoft's working really hard to try and give us a unified client native experience in Maui. Now, this is I talk about web first because it's dominating for a reason. But it's not trivial to make a web client that looks great on phone, tablet, and PC either, right? It's actually pretty hard. And trying to do that in natively is also very challenging. Microsoft's got an interesting set of bits together on this. It's definitely V1, and our experience has been that they don't get it right till V2. Although they'll probably call it version, or V3, although they'll probably call it version 2 because they'll make a 1.1 just to confuse us because numbers are hard. But we're still in the early days of this, and if you've been listening to .NET Rocks, you know I've done a lot of shows around these different client stacks, trying to feel around for why. Why are we trying to find a big native experience? And for the most part, it's because we're being asked to make more apps that work on whatever device the user has. That's the real problem with these multi-client apps. The customer doesn't care. They don't care that it works on a phone and a tablet and a PC. They care that it works on their device, whatever that may be. And we could write it 3 times, but we never get paid enough to do it. So we try and write it once. And that's really stupid. still too difficult to do. But I would also point out another approach to the multi-client technology is the Power Platform. And now, this is not normally a tech that you bring to a set of developers, right? They present this as the no-code, low-code solution. So a couple of things I look at as someone who gets to sort of observe the landscape all the time. There's about 20 different no-code, low-code products out there. Power Platform's only one of them. Oracle's got one. Salesforce has got one. Like, they're everywhere. To me, that says somebody's feeling around in this area. And lots of people are trying to figure out, is there a set of tooling out there that allow us to build the heterogeneous client, so phone, tablet, PC, working against the cloud for typical data over forms problems? Yes, right? That's absolutely in action. Here's the interesting part with the way Power Platforms approach this, and again, we've talked about this a little bit on the show, is that the tooling helps I hate the term citizen developer, it's terrible. How about domain expert? Right? And I'm going to go back to my 90s roots in the VB era, right? Where real developers programmed in C++ and crashed Windows routinely. And then a group of folks found Visual Basic, and they found I can build a Windows app that doesn't crash Windows in the process. But they were typically not developers, right? They were domain experts. They were somebody just trying to do their job better. And they found this tool. Maybe they found Access, maybe they found VB, and they played around with it, and they ruined their career. Because as soon as the boss figured out that you could write VB to do that automation, that's all you were going to be doing from then on, for better or worse, right? And we grew a new generation of developers from that. Well, I see that same movement happening with these tools. The domain experts can sit down and build some automations, generate a set of forms that work across different platforms fairly easily. The smart bit is we, as the so-called pro developers, and I'm not a big fan of that term either, can create more tools for them. So if you want to customize the client experience to fit more with your organization, you can do that and then hand back to the domain experts to actually build up the UI. And the back-end bits, they still need help with that. You could jump through a lot of hoops trying to drag and drop your way through a logic app, where if you can write me a decent API that I can call into my Power App, you can save me a lot of pain and possibly the organization a lot of pain too. Microsoft started to call this fusion development, right? The idea that there's a group of no-code folks that are knocking out, they have that domain expertise to knock out the baselines on these apps, and then we're adding in the bits that need to be there. What you are seeing in the latest round of tools around this now is that it does fit into an existing CI/CD pipeline, that it can be tested, that the code can be properly checked in, deployed, and rolled back like real software, because it is real software. None of us were getting to the bottom of our to-do list anyway. And this is often stuff we didn't want to do in the first place. It's bloody hard. You're trying all these different tools to get there. So if someone's willing to take some of this off your plate and you can build the back-end pieces and the other bits to make it work well, help give them some guide rails to build stuff we can actually maintain, it's not a bad outcome. I'm not saying the answer's clear yet. These are all new bits, but the next few years, this is not going to get smaller. It's going to get bigger. And it can help. Broader strokes, containerization. We're still seeing this evolve. I look at containerization as just the next evolution of virtualization. Virtualization goes back decades. The first versions of virtualization I played with were largely for testing for disparate hardware. And then they became actual production environments to help us consolidate data centers. And now we have containerization, which is virtualization with the operating system stripped out. Now we just have a manifest for all of that. We get that cattle versus pets mindset where we're just you don't fix a machine, you just modify the manifest and build another one and iterate quickly. We're really seeing good tooling in the containerization space for modernizing brownfield apps, for being able to wrap them up into packages. I've been reading a good series coming from some of the Microsoft blogs on taking old IIS apps and putting them into containers, because they need to be protected and need to be broken down into better discrete units than the way they are right now. You don't want them sort of just sprawled across a virtual machine. So how do I get the virtual machine out of these old apps? Containers seem to be working in that direction. I think we're going to see containerization push down more and more into the operating system level, where individual apps are essentially going to be a virtual instance, could be run anywhere. You don't really know and you don't care. that you can put that, it might be a piece of virtual desktop, might be a piece of a virtualized app. It doesn't matter. You'll be able to do that. Just keeping apps away from each other because they behave badly. But also recognizing we don't get to rewrite everything. So let's put the things that are still important but not rewritable in small enough boxes that they can't hurt anybody. So we're going to see more of that. If this is feeling a little overwhelming, that's okay. We're in an industry that changes very rapidly, but we don't have to. We get to choose. I've been doing this long enough now. I am not that excited about the new bits. I'm not racing out to try every new thing every time anymore. Because there's more than one way to have a career. And in fact, your mode of career is going to evolve as you age and change. You can grab the new bits every time if you want. You ready to jump on the new stack? I'm going to talk about a bunch of new stacks coming up. That's great. But we also value experts in an existing stack because those stacks don't go away. The pool gets smaller, but the number of people also shrinks. Ask a COBOL developer how busy they are right now, because the COBOL stuff didn't go away, but the training sure did. And now I'm meeting late 60s, early 70s, making more money than they've ever made in their lives, really would like to retire, but aren't going to give up the cash. And so it continues. This could be ASP.NET Web Forms. That tech's been around a long time. A lot of code is being written, and it's not all going away. And so there may not be as many Web Forms developers, but there's still a need for them. And so you're in an interesting little space. I would say it doesn't mean you stop learning. Do address the modern problems. Right? How do I make web forms work well on a phone? But how do you address that problem space, right? And be aware of that, where that is. And if it, hit a point, be the one that knows, okay, this is the point where you're against the edges of web forms and you should really think about how we migrate that to something else. Or keep it maintained. It's also a good career. There's a bunch of ways to do this. Just pick the things that matter the most to you, work hard at being the expert on them, and you'll be the important man, you'll be the bigger fish in a smaller pond. It's still a good gig. Or be in the new pond, where everybody's a small fish and we're all racing around trying to figure things out. There's one way to have a great career. You can try. You can experiment. You can live in different spots. Okay, let's talk about artificial intelligence. And I show how for a very good reason. Artificial intelligence is an extremely old, very abused term. It comes from the 1950s. Marvin Minsky, Dartmouth University, he was trying to raise money from the military building automation. He succeeded, but that's the first time the term artificial intelligence is used. We don't hear it until HAL, until 1968, 2001, A Space Odyssey. That's the first time the general public heard the phrase artificial intelligence, and then it tried to kill everybody. Setting up our relationship with artificial intelligence, right? That's just how it's always worked. Terminator, it's all the same thing over and over again, right? The tropes make us weird about this. Here's the way I talk about artificial intelligence. AI is the term you use for a technology that doesn't work. The moment it does work, it gets a new name. It becomes predictive analytics or vision systems, right? There's all of them. As long as it doesn't work, it's AI. When it does work, it'll be peeled off. And this is actually a very clever graphic because the shortest lines, the planning, scheduling, optimization, that's the tech that Minsky worked on in the 50s for the US military. Expert systems came in the 1970s. The original speech recognition systems of the late 80s and 90s. Those are the ones you had to train over and over and over again. Then we got into better natural language processing, and then you get these latest lines. About around 2011, 2012, we had a new generation of neural nets appear. That's when stuff like Siri turned up, where now you didn't have to train for speech. It just worked, right? It was a machine learning model trained on a huge amount of voice so that it could recognize anybody's voices, except Australians. And I say that, it's kind of a joke, not actually a joke. That was the one area it didn't work all that well on. And you can incorporate these various technologies, machine vision and so forth, into your software. So if you've got a reason to recognize objects, you can do it. It's my favorite recognition system of all time because it is absolutely correct. Right? The software did what it was asked to do. It looked at the picture and found all the instances of dog. And this is an interesting idea, and I've seen customers starting to do this, where they're now, the big thing with a smartphone or even a tablet is you're taking the device to the work. As long as we were living in the PC land, you always brought the work to the device, right? It was strapped to a desk. And so, everything came into your inbox and then you processed it and it went out an outbox. But as soon as you get into those small form factors, now they're going to the work, and suddenly things like cameras and recognition becomes a big deal. And we've got software for this. You don't have to be a leading edge developer to do this. Spend a little time in cognitive services. The image recognition systems are pretty darn powerful, and they can tell you this one dog is 3 dogs. Same with the chatbot thing. I'm not a huge fan of chatbots. Nobody is. But again, if we're doing more with less, first line tech support as a set of bots, this is not that difficult to build. The natural language processing stuff is solved. You basically have to build up a large enough glossary of information to answer appropriate questions, but it's very cost effective to be able to deal with a lot of the dumb questions that come in rather than involving people in them. And so they hit a point where they have to be escalated. That's efficient work, and it's modern AI for better or worse. More on the edge of what's happening right now, Microsoft's been playing with this thing called the form recognizer. So this is a vision implementation system to recognize forms fields and then actually turn them into forms fields. So being able to scan a paper form and just have it fill it in a digital form. My thought on this is, so why can't I just point this at a web app and have it turn it into a modern app? Because it's just forms on a screen, just like the paper. What's the difference? So this seems very obvious to me that this is an automation path to modernizing software and to modernizing workflows, where we get rid of the physical forms and go more digital all the way and be able to switch over quickly. When young folks ask me about what areas to get into in computing, the biggest opportunity space, I tend to talk about data analytics because it's still well behind. We've had predictive analytics for decades. It was just very expensive and complicated. You had to do a lot of planning to build up predictive analytics systems, but that's just not true anymore. Part of that is cloud, that today we have enough compute that all these different predictive analytic models like clustering and sentiment analysis and Elliott waves and so forth, instead of having to figure out with math which one you should run, just run them all. It's just cloud compute. It'll cost you a few dollars against a given data set, and then you look at the results that make the most sense. So we've got good automation around that, and then you throw in machine learning on top of that. It has machine learning models that know your data better, that have learned against it to be doing even better predictive analytics. Today, the sexy is called prescriptive analytics. So this is cycling through predictive analytics with actions. So now we build up a set of actions. So you've probably experienced this whether you knew it or not. Lately, I've found if I throw a bunch of stuff into a shopping cart and then close the page, I get an email from them sometime later about, hey, you threw some stuff in the cart there. How about a 10% discount? All these tickler emails. There's no person involved in any of that now. This is the predictive analytics model where they're trying to predict, if I send you this tickler, does it get more results than this tickler, right? And there's a set of stages. You gradually build up a tree. But this is all yield stuff. This is how our software makes the company more money, right? That we increase the retention of customers, that we get them to buy more and we get them into other products. And so but you can't guess. You can't figure this out for yourself. What you got to do is let the data do the thinking, right? The machine learning models try all these different things, look at the result, and then tune our own model. It's not easy stuff to do yet, but you're seeing a lot of places. And of course, I've only talked about e-commerce. You're starting to see these kinds of prescriptive analytics being used for things like hardware maintenance. When do we take a gas turbine down for repair? It's not necessarily when it's worn out, but when it's going to be the least used, or we have enough backup that it can be down for a few weeks. So we might change out parts that may have another 6 months on them, just because we don't want to wait till it's too late. I saw a bunch of this prescriptive work done around the California wildfires, where they're trying to figure out, you kill a certain number of people when you evacuate them. So can you evacuate them earlier at lower stress, so you're less likely to cause heart attacks and things? Even though it's more disruptive, it's ultimately less costly. So they're starting to use machine learning models against that kind of data to save lives. It's an area that needs more explanation. We have more data than ever before, but we know less and less about it. And it's because we only have so much time, but the tools are getting smart enough and inexpensive enough to really be used. A lot of this machine learning models, they're cloud services you can run for a few dollars for a week and then shut off if it isn't doing anything for you. On the development side, we've got the OpenAI guys, and if you want to build another version of Asteroids, you can. You just write out descriptive text of what you expect the game to do, and it writes the code for you. That's fun and amusing, but the far more relevant one is Copilot. If you spend a little time with Copilot, you learn pretty quickly, yeah, I don't have to write a lot of this code, but I do have to write very clear instructions for what I want to have happen. So this is just an amplifier for us. It's another tool. It's a way to find code quickly. Right? That's sort of like a super Stack Overflow in a lot of respects. Where this is getting crazier now, if you haven't had a chance to play with this stuff, you get, now it's $10 a month. It was free for quite a while, but you can do a trial. It takes time to be expressive enough with Copilot to actually get useful results out of it. But for a lot of plumbing and routine code, it's pretty good. It just needs an operator, right? This isn't replacing anybody. This is just speeding up your rate of experimentation. Now, it's not like they're holding still on this yet. They just announced that Copilot for Power Platform. So now we're having domain experts going to start describing what they want to have happen. And then they've now just announced, hey, GitHub. Because as if we didn't have enough stuff to talk to, now you can talk to Copilot. Because it turns out writing out those descriptions, too much work. Just talk. So this is in preview. Tied to Copilot, so you can just try and describe things. Again, the news will grab onto this and say, developers are obsolete. I have heard that many, many times. But when you recognize the bottom line for a developer, what they really do is take a business problem and turn it into a technologically solved problem. Somebody has to say the right words, write the right thing, test stuff out, evaluate that it's actually providing value. That's us. It's always been us. It's just another tool for doing it faster. Other new technology. What's going to replace the smartphone? Because the smartphone's kind of done. It's been a slab of black glass since like 2007. Before the iPhone came along, phones were kind of fun. They'd pop out keyboards and little attachments, and they were cool. Now they're all slabs of black glass. They're bigger, they're smaller, they're longer, they're taller, higher resolution, lower resolution, 1 camera, 2 cameras, 3 cameras, 5 cameras. They're all kind of the same. But what they've really done is completely penetrated civilization. Everybody's got one. So it's ripe for an evolution. We're kind of stale. And you can see the industry feeling around for this. The obvious candidate to replace the smartphone is the glasses, the goggles, the visor, some kind of augmented reality. This is a mock-up of what people think Apple's going to announce someday soon. There is no evidence that this is true, so I show it to you as a lie. If you want real ones, there are real ones. This is Qualcomm's XR1. So it's a pair of glasses tethered to an Android phone. It's about $1,000. Cameras facing outwards, writing data directly into your eyes, microphones and earphones. If you like to go more the Google Glass look, you can go with Toshiba's DynaEdge, more the industrial style. Or there's HoloLens. Microsoft's wildly overdue to make another HoloLens. Alex Kipman's now left the company, so it's going to be a while, but HoloLens was an extraordinary device. It still is. It's still for sale. It's still $3,500, which is not the expensive part. The expensive part of companies running HoloLenses at scale, it's about $1,000 per month per device in cloud costs. Now, for certain verticals, this makes perfect sense, right? If you're maintaining high-end industrial equipment, the fact that the AR device can basically make the unit transparent to you, can have your checklist live, can actually see that you finished a maintenance step physically and check it off for you, that you can request an expert who can now go in their HoloLens from a different location and look through your glasses at what you're working on and give you advice. This is pretty profound work for certain verticals. So you talk about Pratt & Whitney which builds jet turbines for airliners. Those are $50 million devices. And then they do a $5 million maintenance cycle on it. The fact that they use a bunch of $3,500, $1,000 a month headsets makes perfect sense, because the glasses allow them to show a detailed record of exactly the maintenance being done, what parts are replaced, that those parts were authentic, like all of the problems that they have addressed with this device. And the HoloLens is now several years old. It's a fully contained computer strapped to your head. It's right to be modernized. There's several talks behind from Moore's Law perspective. It can have denser chips, it can have better batteries, it can be lighter and smaller and faster. Bigger field of view. There's lots of possibilities there. This is an area that's about to take off. It reminds me of the BlackBerry in like the 1990s. So a company called RIM made this smartphone in the 90s, the BlackBerry. It had a keyboard on it, and you could get email on your phone. Let me say it again. Email on your phone in the 90s. Okay, now we all have email on our phone, and we wish you didn't, but back then it was a big deal. Now to pull that off, you had to own BlackBerries. They were about $1,000 a crack in the 90s. But you also had to run a huge back-end service. You need a customized version of Microsoft Exchange with all the BlackBerry enterprise extensions. You need a couple of guys in white lab coats to keep the thing alive. But your executives got email on their phones. They called them crackberries because everybody was crazy about them, right? They were expensive, they were complicated to maintain, they tended to be for senior people in large organizations, much the way that we look at AR devices today, the HoloLenses, for specific verticals, for specific applications. The path from the BlackBerry to the iPhone is a reduction in cost and a diversification of its technology. We're a ways away from that yet, but it's absolutely apparent we're on that path. And when that comes along, that's a gold rush for us. Talk about a crazy time. That's a whole new class of iFart apps we haven't written yet. More importantly, the phone fundamentally is still the same interface that we're used to, right? Screen, keyboard, mouse. Screen, touch. Kind of the same. Now being a 3D space. That's a different interface. It's going to be hard to do that well. What information is well represented that way? What work is better served that way? That's the things we're going to struggle with. But the ones that get it right are going to do very, very well. And that's just the next few years. That's imminent. Let's talk about Meta. Because they're trying with the metaverse. It isn't going well. Now, part of that is recognizing a year ago, our friend Mark Zuck was smart enough to recognize that Facebook was already doomed, right? We're all the product, their actual customers or advertisers, that was already dying. So it's not that he had a divine inspiration to try and make the metaverse real. It's that if he didn't do this, he was dying anyway. And the consequence of a year's worth of effort is reducing the value of Facebook by $650 billion. I know the FTX guy lost $16 billion, but $650 billion. That's a hell of a case study. And now what? They're going to lay off 11,000 people. They are trying to find the 3D internet effectively, right? Now, we had Second Life 20 years ago, but we're trying to find the workspace on it. The problem is you don't get to start with social media. Nobody wants this. And I actually think it's held back the evolution of the metaverse, primarily because people don't want to be associated with Facebook. Now, I do know there are companies that are looking in the enterprise space for what's better represented with these goggles, what kind of workloads make sense. The headsets that Meta makes are pretty good. The Quest 2 is easily the best VR headset out there. It's self-contained, it's a few $100s. They've just announced the Quest Pro, which is $1,500, so I don't know how many of those you're gonna sell. But Microsoft also jumped on board with Teams for the Horizon workspace. So collaboration in 3D, without legs. That's one of the things. Nobody needs to see your legs. If you want to get into the space, you can today. The most popular programming environment for all the AR stuff, Unity, C#. It's not the only one. You can go work in the Unreal Engine if you'd rather live in C++. But if you think this stuff's cool and you're looking at the opportunities and you want to think about what business can do in this space, spend a little time with some Unity training. It's not that difficult, and it is interesting. And spend a little time in a set of VR goggles or play with the AR goggles. They're all there. All right, we got only a few minutes left. Let's go to the fun stuff. Let's talk a little bit about quantum computing, because people ask all the time. Now, quantum computing is a supercomputing problem. So, I talked about the Frontier supercomputer. What do they do with that machine? Mostly they're problems like weather prediction and fluid dynamic modeling. If you want to build a high-efficiency airliner wing, you use a supercomputer. And if you want to accurately predict hurricanes, you use a supercomputer. And quantum computers are a particular class of supercomputer. They're the kind that doesn't work. They're trying to solve, it's a very difficult problem, right, to actually make these things work. Getting quantum entanglement means typically cooling things with liquid helium. So you need to build a room for your quantum computer that stores both liquid nitrogen and liquid helium, because you have to use the nitrogen to cool down the device enough to be able to put liquid helium into it. Liquid helium is only liquid at a couple of degrees temperature range, then it turns back to a gas and makes things explode. So you need venting systems to manage when you screw up, because you're gonna. They're not easy things to own. Now, we've had some breakthroughs. A couple of years ago, the Sycamore processor by Google, with 54 qubits, although they only used 53 for the run because one of them was broken, managed to do a particular problem, solve a particular problem they thought would take 10,000 years for a conventional computer to solve. It was eventually determined they could figure it out in 2.5 days. IBM proved that, but they did it in 200 seconds. So, okay, an achievement. The Chinese, with a photonic quantum computer with 113 qubits, did a boson sampling analysis that we already knew the answer to, but it was the kind of compute problem that if you were going to do it in traditional computers, it would take billions of years. So pretty clearly a success in proving quantum computing. That was 2020. And now IBM, with their Eagle processor in 2021, using transport architecture, they've been running some trials. So they're up to 120 qubits, which is pretty good. We think the action gets interesting in the few hundred qubits, 300, 400. We start to get meaningful results. This is very difficult compute problems. And really the question is, we've only done sample problems that aren't that interesting. What are the real problems that matter? Like, what could we do with a quantum computer that anybody cares about? And it's not breaking encryption. Breaking encryption actually takes a very, very powerful quantum computer. Long before we'll be able to do that, we'll have other use for quantum computers. But more importantly, quantum computers are only good at breaking encryption that's based on primes, because they're good at primes. There are encryption strategies that don't use primes. We're already starting to switch them on the threat that could eventually be destroyed. So don't worry about the hype around the whole ending of encryption thing. There are solutions. We're working towards them. But let's actually solve some real problems. My current favorite problem is a quantum chemistry problem. It involves agriculture. Now, we know in ancient agriculture, we had to rotate crops, right? You would grow, if you just kept trying to grow wheat on the same land year after year, season after season, you deplete the soil. Now, today we have industrial fertilizers. We use the Haber-Bosch process developed around World War I, because it also makes explosives, to refertilize the land. But before we had industrial fertilizers, this is 1% of the world's energy consumption is used to make fertilizers, to make food. But before that, we used to rotate crops. And the crop we typically rotate in was a bean, because on that bean, on its roots, was a rhizome. And that rhizome is a symbiotic bacteria that actually affixes nitrogen. It has an enzyme inside it called nitrogenase. We've studied this thing for 200 years. We roughly know how it works. That this enzyme is able to grab oxygen from water and nitrogen from the atmosphere and make it into ammonia in the root of the bean. So you grow beans for a season, then you pick the beans, then you plow the plant under, then you let it sit for a year, and it actually fertilizes the soil, and you can plant wheat again. It's not as good as industrial fertilizers, but it definitely works. It just takes longer. We know that inside of that enzyme is a catalytic reaction between iron and molybdenum that does the affixation of ammonia. We just can't figure out how it works, because it's a compute problem that has 2 to the 170th complexity. There are only 2 to the 150th atoms on Earth. So this is a problem outside the scope of classical computing, but a quantum computer should be able to knock it out in about 3 or 4 minutes. Now, if they solved it, we would then know what the catalytic reaction is. It doesn't mean we know how to reproduce it, just that we know what to look for. And that's enough. That typically now it becomes an engineering problem of, can you reproduce this? And if you could, what would it mean for civilization? We stop making industrial fertilizers. I can imagine a little spike with a watch battery or a little solar panel on it that you put beside the plant that both measures what's in the soil and then pulls from the atmosphere the ingredients that the soil needs to fertilize it plant by plant. no wasted fertilizers, no tractors spraying them. It's a big change. And that's one quantum chemistry problem. Batteries. We basically batteries through alchemy. We just combine different ingredients and test it. We've gotten better at testing rapidly, but we don't really know how batteries work. Quantum chemistry problem that we could solve and make batteries dramatically better. Superconductors. You remember them from the 80s when we got the Rebso superconductors, these ceramic superconductors that we poured a little in like on the cube will float. We kind of don't really know how those work either. It's a quantum chemistry problem. We spent some time on the quantum chemistry on this. We could get superconductors up to higher temperatures where they didn't need to be cooled at all. That changes how we distribute energy. These are big, hard problems, but they're all deterministic problems. Like if once you solve it once, you're kind of done, which begs the question, like how many quantum computers are we really going to need? We're still looking for non-deterministic problems that quantum computers need. Most of them are deterministic. You kind of get back to that idea that Thomas Watson, well, this is a apocryphal quote, when he was the chairman of IBM in the early days, when they were going out to sell their first mainframe, and he thought maybe there's a market for 5 of these, and he came back for orders of 20. It's hard to understand when your computer looks like this, how many you're going to need, right? In those early days of the mainframes, they hadn't made the transistor yet. The computers were all bespoke. Each one of them was different. They used relays or they used vacuum tubes. There's a bunch of different ways to create a bit. They hadn't settled on the silicon bit yet. That's where quantum computers are right now. Each design is different. Each machine is bespoke. Different ways to make qubits. We haven't actually come up with a stable qubit. And when your computer looks like this, you can't envision the smartphone. You can't even see it. When Bell Labs made the first transistor out of germanium, this is what it looked like. You know, how do you picture an M2 with 20 billion of those in a 5 nanometer process when this is your transistor? They didn't know. One of the guys that worked on that transistor is a guy named William Shockley. Apparently not a very pleasant man, very smart. And after he built the transistor, he thought it was possible to make them out of silicon and put them into substrates. And he created a company called Shockley Semiconductor in an area of Northern California that would eventually be known as Silicon Valley because of Shockley Semiconductor. And he actually used mainframe computers of the day, those mechanical computers, to help him model how to build the silicon substrates with doping, to use phosphorus and arsenic to actually shape them, which is why the land in Silicon Valley is poisoned. All that stuff they just dumped in the ditches. But it began the chain that leads to our careers, to the microcomputer, and ultimately to quantum computers. We don't know what the perfect qubit is yet. But these weird, fragile qubits we're building, they might be enough power, enough unstable power to help us model the reliable qubit so that we could actually see what the M2 in quantum computing is. And here's what I know for sure, because it's hard to see the future when you get this far out and you just have a tough time imagining those things. What comes after this is what we choose to make. Moore's law only happens because a whole lot of people work really hard to make it happen. We're the folks who choose. We get to make the future. It's up to us. I can't wait to see what we make. Thank you.